Hi and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack! In the last episode, we did some cleanup and increased the allowed reminder size we are willing to take into our BSmooth values. Also improved our prime construction time. Now we have several magic numbers in place that we need to optimize. We have the B number, which is the BSmooth bound that determines the largest prime size in our base. That number, we start a new episode. So last time it was 80k. Have the range that it's used in find BSmooth values. That range, that's like this range, and we have the reminder size. Reminder, yeah, it's that value. So it's the biggest prime in our prime base multiplied by some magic number. Max prime. And then we are taking the square root of it, the approximation of the square root of it. And then we have 1.5, the multiplier of the prime base size that determines how many values we are willing to take into the BSmooth collection before we start solving the metrics. So during this episode, I would like to get rid of this number. When I'm running in the last episode, it finds 5,662 BSmooth values. When I'm optimizing, well, the entire thing, I found that the actual value it's 4859. When I'm running that, then it needs to find only 4,860 values as opposite to that value. So we need to search for less BSmooth values, and this is big. Like, well, I assume that it's big because we are going to run on less iterations and we will finish our loop earlier. So to do that, I want to introduce you into continued factorization. This is my original idea. It doesn't mean that I was the first to discover it, but it means that I'm not aware of anyone else doing anything similar. So let's see how it works. Basically, instead of doing the metrics phase at the end, we will continuously be doing it for each new prime we are finding. But the metrics algorithm is expensive one. It's n power 3, O of n power 3. And so to change it, I created a new algorithm, and it works as follows. So we have a continuous input of the BSmooth value. And for each of those values, we do the following. We save it into a BSmooth list. We are building this list gradually, as well as our solution matrix. The solution matrix needs to be of the size of the BSmooth list. So each new item that it's added adds one new row to the solution matrix. And it's saved to the BSmooth list. Then for each bit that it's set in the vector of the BSmooth value, we will try to eliminate it with the already found eliminators. So at the first iteration that's supposed to be empty, but let's continue reading and let's see how it's used. So we are eliminating, basically we're just eliminating everything that we can from that BSmooth values that we are getting. And then after eliminating all of it, we are left with two options. Either the BSmooth value is a new solution that we are ready to extract, or it becomes a new eliminator. And there is really no third option. So this is that new process, next process of eliminating everything with that new eliminators that we found. So first we are testing if the vector is empty or null, then it's a solution that we are extracting. Otherwise, we are using it to eliminate everything that we have in the BSmooth list. So first we are adding it into eliminators map for future use. And then we are iterating over BSmooth list, checking for each BSmooth value if it has the bit on as the first one bit of the eliminator. So eliminator is a BSmooth value that have everything set to 0 except values after some point in the vector. So for example, eliminator can be look like that. It really doesn't matter what happens after that one. It can be used to eliminate everything that has 1 in index 4. Because everything before 1 is set to 0. So it will eliminate everything in the BSmooth list, which include also other eliminators. Then every item in that list that was eliminated can potentially become a new eliminator by itself. Again, why I deleted the example. Do, yeah. So after that becomes 0, it can be a new eliminator with index 6. So we are doing this process recursively for every item we found in the BSmooth list. Now, last time that I implemented that thing, it took a while. So this time I did a little bit shortcut and I already prepared a solution for it. Matrix 3. I'll just walk you through the source code and explain how it works, and then we will integrate it into episode 8. So first we're adding the BSmooth value. We're then adding it into BSmooth list. Then we are creating a new row, a new vector, which we represent with a bit set. We are setting the last item in it, and then adding into the solution matrix. Let's call it add to solution for clarity. It determines the last row and increase the solution matrix by 1. And it doesn't need any parameters because that's completely dependent on the BSmooth list size. Okay, then we are iterating over the vector. The size here it determines the index of the last set bit index, and then we are checking for each item if it's set. If it's set, we will try to eliminate it using the eliminators map, which is a hash map mapping the index of the eliminator, it's the value, and the key is the index of the set bit. This is the eliminator bit index. Yeah. When we are XORing, we're getting eliminator index and the BSmooth index. We are getting the BSmooth value from the BSmooth list, same as the eliminator. Then we are XORing the BSmooth vector, and also the solution matrix, we're also updating it. Cool. Now after that, we add the eliminator. If the eliminator vector is empty, we can extract a solution. Otherwise, we found a new eliminator. So we extract the eliminator index. Eliminator bit index. And then with eliminator bit index, we are adding a new entry into the eliminator map. And then we're iterating over all the items in the BSmooth list and trying to eliminate them, with one exception that we are not trying to eliminate ourselves. Okay, now this portion, just because we eliminated an index in a vector, it doesn't mean that it will turn into eliminator, because it could be that it had, let's suppose that we are eliminating the vector, that this is the vectors that we are eliminating, and it has one set on its third index and fourth index. Now our eliminator eliminates the fourth index. This doesn't turn this vector into eliminator because it already has a bit set in here. So it doesn't change it. And this is the conditions that we are testing here. And if it's indeed turned into eliminator, then we will add it into the list of eliminators, and which is defined here. And then we will recursively call this method all over again. Cool. Now for the solution extraction, I took the logic that we had outside and I just placed it here. It will just compute the A and the B value as we did before, and test the solution, which is, if not trivial, then the GCD will give us a divisor of n, non-trivial divisor of n. Okay, so this is the new algorithm. In terms of performances, I think it works. It have the same performances, with one difference, that it doesn't using the filtering phase like we had in here. So in our previous solution, we had filter single primes. So primes that don't contribute to the solutions, that they have a bit set in some place that cannot be eliminated. And so those vectors can never be part of the solution. We don't have this optimization anymore. But what we do have is a save in here. So instead of searching for eliminator index, we save this because we have defined eliminator. We save this because we have a map. But in here there is a ON operation, which is not doesn't really count because there is ON right next to it, so it doesn't increase affect the performances, but a minor optimization here and a minor bad a good optimization that we are not using. Okay, so now let's integrate it. So if we want to have a continuous process, what we need to do is to start working with threads. And the way of doing that is to work with executors. Well, one option I'm going to use. And we're going to use it, let's see well. First we're building the prime base. We have the position, we're building the wheels. Oh, let's add logs here. Build wheels. Then we're searching for smooth values. And everything that happens next needs to go away. So this is the part that was added to the matrix itself, the solution extraction. And we don't use the version 2 anymore. And the extraction of the vectors needs to happen in real time. Okay. We also will not need that collection anymore because it's managed inside the new matrix. So let's define it. It requires one setup, and it's give it the end, so it will be able to do the solution extraction. And then during the iteration of the BSmooth values, we don't have this stop condition anymore. And the addition of the new value, that part goes into the executor. So let's call it a add BSmooth value. Okay. So now we are on the matrix thread. So we need to call the matrix and add a new BSmooth value. But before that, we need to extract the vector. Call it B. It's called to extract vector out of V. The vector could be null, so let's avoid those. If it's not null, then let's construct V. Let's construct BSmooth, our vector, and add it to the matrix. Now inside the matrix, when extracting a solution, it's called to system exit. If solution is found, the program will terminate. All right, it seems like this is it. Yeah, we don't need that anymore. And that can be final. What else? Oh, and the while loop, yeah. It doesn't aware that it actually terminates. Okay, Let's see if it works. Yes, it is working, and we found 3389 BSmooth values. In the previous execution, it was 3926 extracted values, 89 BSmooth values. Yeah, I would say close enough because of we have two. Yeah, we have two threads running simultaneously, so I assume that that's valid. It's certainly smaller than this number. So awesome. We make this improvement. If you have any questions, please post them in the Facebook group. The source code is going to be available on GitHub. See ya.